Yeah, so the setting of the inverse function theorem is that I'm given a differentiable function from an open set in Rn to Rn. And the crucial hypothesis is that f prime of A, remember, this is going to be a linear map from Rn to itself. And let us call that this is A, capital A is invertible. And f prime is, remember, this function is defined on all of you because f is differentiable. But I say that this function is also continuous at A. So all of this is given. All of this is given. Then the conclusion is the following. In short, so the conclusion, when I write it, it's going to look a bit long because I'm going to break it up into steps by which we are going to prove it. But in short, it is going to say something very simple, that this function f is actually going to be a local homeomorphism, and moreover, it is the inverse of it is also going to be have the same properties of f. So what does that mean? Let's write this down. So 1, f is injective in some neighborhood. It may not be globally injective, but locally it is going to be injective. Look at the function, for example, y equals x squared. If you look at any point other than the point 0, then the derivative of this function is going to be non-zero. As a result, it is going to be an invertible map from R1 to R1. And in fact, it is a good idea to see what this theorem is saying in n equal to 1 case, where the statement is much easier and the proof is also much easier, which you should be able to do by hand. Today's proof is going to have a number of steps. If you sort of get confused, then you can fall back to n equal to 1 case and see what the proof is saying. All right. Now, the second one says that the following. There are open sets, and this open is the keyword over here. V, which is mu, and of course containing A, and W, which is in the target Rn, W containing f of A. So all I'm saying is that such that, remember, by step 1, by claim 1, f is supposed to be an injective function. So what I'm going to say is that f restricts to a bijection between V and W. So such that f is, so in other words, W is just f of V. But the key point is that W is also supposed to be open. So f is a bijection from V to W, f. Whose inverse, so let's call this C, say G. Is also continuous. A continuous function, even if it is invertible, it's not necessary that its inverse be continuous. This may be a new phenomenon if you have not seen this before. For example, you see, if I have a linear function between two vector spaces, a linear map, and if the map is invertible, then the inverse is automatically linear. That is not the case for continuous functions. You can see, for example, the function that takes the interval from 0 to 2 pi, which is closed at 0 and open at 2 pi. you call an element in that to be theta, and if you take this to sine theta, cos theta, sine theta, then you will see that this function is a perfectly beautiful continuous function. But the inverse is not continuous because it has to break the circle open in order to get the initial half open, half closed interval, whose inverse is also continuous. A remark here. So let's just see a side note here. A bijective continuous map whose inverse is also continuous is called a homeomorphism. Notice this is a different word from homomorphism. Homeomorphism, just a word. And so this 2 is really saying that F itself need not be a homeomorphism. F need not even be bijective, but it is a local homeomorphism. Is a and I'll put this in quotations. It means exactly what it is saying. Local homeomorphism means that at this given point A, you can find a neighborhood on which it is a homeomorphism. Okay, homeomorphism onto an open set in R. And number 3 is that F inverse is also differentiable. Is differentiable on this W. And since it is differentiable, you can calculate the formula for the derivative of the inverse just by using the chain rule. And it is the expected formula. So remember, we have called this function G, right? So what is going to be the thing? df inverse at any point f of, let's say, x. What will that be? The derivative of the inverse is going to be the inverse of the derivative, right? Because remember, the derivatives are linear maps. I.e. for any f of x in W. So what will be the formula? This will be the same thing as the derivative of f evaluated at x, and then what?
Whole inverse.
All of that inverse. All right. So there is a lot to understand. Just in terms of the meaning and also the proof. So let me make some remarks. So one is that crucial that dimension of U and target, dimension of the source and target are the same. Otherwise, what does it mean for the derivative to be an invertible map? It's a linear map. It needs to be between vector spaces of the same dimension. But there are appropriate generalizations or appropriate versions, let me say, not of the theorem when f prime of A is Instead of being invertible, it is just injective. Or even arbitrary. You have to make the statement, modify the statement suitably, but the statements also become a little more complicated. The second version, when f prime is surjective, we will call that the implicit function theorem. So these things may seem more general, but they can be deduced as a corollary of this inverse function theorem that we are proving. So appropriate versions and these versions can be proved using the above theorem. So this is somehow a crucial case to understand. And finally, okay, so n is equal to 1 is easy. And you should do this proof for yourself. Essentially, it will boil down to, as many things do, it boils down to the mean value theorem. So do directly using mean value theorem or follow the proof here if you sort of don't see what is going on. Okay. And then this last last comment, and let me say this here, which is that we can sort of normalize what is going on over here. So let me say what that means. We may assume that a is equal to 0 and f of a equal to 0. How do you do that? This is just a shift, right? So replace f by the function f of x plus a and then minus b. Notice that if I plug in x equal to 0 in this function, then I'm going to get f of a minus b, which is 0, by the way. So b here, I haven't introduced the notation. And in fact, let me know. So it's f of x plus a minus a, etc. But more interestingly, we can also scale this. This should remind you of what we do in to get mean value theorem from Rolle's theorem, right? You just adjust it. So the scaling is to ensure that the derivative is not just any invertible matrix, but we can even make it identity. F prime of a is equal to identity. So how do we do this? Suppose the derivative of a function at some place is 3, just an ordinary real valued function of one variable. If it's 3, if I want the derivative to be 1, it's very easy. I just scale the function by, multiplied by 1/3. So here it's the same thing. Replace f by f prime of a, the whole inverse, times f of.
So are we doing a basis change of both the spaces?
Well, yeah. So in this case, it is just, you can think of it as basis change. But I can also say that the basis stays the same. I'm just changing the function.
Oh, okay.
Replace. Notice what is happening here. This may look like multiplication, but really it's a composition, right? F is a function from u to Rn. And I'm simply doing after that the inverse of the linear map, which is the derivative. So this is an exercise for you. Check that the result for given f follows easily from the result for such normalized. And this is okay, no? Because you see, what is the normal? Let's look at the nature of the result just to see what is going on. Okay. Now, the function that I am defining, what am I doing? I'm shifting in the domain, I'm shifting in the range, and I'm multiplying by an invertible matrix. All of these are themselves bijective maps. So whether the original map is injective or not in some part is not going to change. The open set under consideration may change, but the part 2 is asserting existence of open sets. So those open sets I can change whichever way I want. It's up to me. And notice that these maps, not only are they bijections, they themselves are continuous bijection, like both ways continuous bijection. Shifting, I can shift back, and shift is a continuous map. A linear map is continuous. And if this linear map is invertible, then the inverse is a linear map. That will also be continuous. So nothing is really affected. But if it is not clear to you, you can sit down and convince yourself of this. However, and here's the point. So this normalization makes some formulas and calculations in the proof a bit simpler. And this is what many sources normally do. But I do not want to do that for the following reason. Obscure a bit. You know, the natural main idea. So we won't do this. When you're seeing some meaningful proof, if you have some sort of rabbit pulled out of the hat, then it is always like, wow, how did they think of this? Sometimes it is better to give a proof that is less slick, but you actually see where somebody may have had those ideas. All right. So with all of that said, let's actually jump into the proof itself. So steps. So proof. And we will follow the same steps. First, it's the injectivity of f in some neighborhood. So 1. So we will prove the injectivity on injectivity of f on a ball B around A. The word small doesn't mean anything. It's only psychological. Of some small radius epsilon that we will choose later. Okay. Remember, the theorem only asserts existence of these neighborhoods. So I can make these neighborhoods as small as I want. If something works, then anything smaller will also work. We'll choose epsilon later. Now, here is the point, very simply. What is the best linear approximation for f near A? Best linear approximation for f of x near A is what function? This is from the first time you encountered the tangent line. And that's very easy, right? So this is f of A plus
f dash of A x minus AX minus A.
Correct. And now we have to sort of understand that this looks exactly the same as what you wrote in school, but this second term is a, so here, let's just n by n matrix times column vector. That's what this is. Okay. Now just imagine for a moment that the function f of x is actually equal to this function. Then we can just repeat the discussion that we had in this normalization business. So the function, what is this function? You take x and then you shift it by a. Then you multiply it by a matrix, an invertible matrix, and then again you add this vector. You see, all of these steps, all the steps that I have done here over here are invertible steps. So the entire function itself is invertible. In particular, it is injective. So if f of x were actually equal to this, I can't say linear function, it's an affine function, right? Because I'm shifting, then multiplying, then take multiplying by matrix and then shifting it. So it's an affine function. But okay, I mean, the entire theorem is kind of obvious for such a function. So the idea is that, okay, if the result is obvious for such functions, then the given function is maybe not too far away from this function in a small neighborhood. So let us examine the difference. Let us examine the remainder, and hopefully we can show that the remainder is small enough so that the desired properties are not violated by this small diversion. So let me write this. If f were equal to this function, the theorem is easy. So let's examine the error or the remainder. And what is the remainder? Let's call this some ad hoc notation for now. R of x equal to f of x minus f of a minus f prime of a times x minus a. Okay, very good. So how rapidly is this function changing? Let us see. What is r prime of x?
Prime of x minus f prime of a.
So f prime of x minus f prime of a. Okay, good. So several things to note over here. One is that as far as this r prime of x was concerned, the term f of a and then the minus a in the x minus a, they didn't really play any role. No? They just sort of went away. So I could have taken. So first, let me write this down. I want to show injectivity of f, right? So let us see how r behaves when I take differences. So r of x1 minus r of x2. What is that equal to?
Prime of x1 minus f prime of x2.
Correct. No. So this is no. So I'm calculating the difference between values of r, not values
Sir,
of
fx1 minus fx2 minus f dash a into x1 minus x2.
minus and f prime of a times. Really, we should, we are abusing the notation here a little bit, right? This f prime of a times, that times really is, I mean, if you want to think of it as times, then you think of it as matrix vector multiplication, right? Otherwise, it is evaluation of a map on a vector. Okay, so times x1 minus x2, correct? The a terms are just going to go. So we could have taken, instead of this r, we could have taken, so aside, f of x minus f prime of a times x. This above difference would have been the same. So this is just an aside. But now here is the kind of so what I want to do is I want to estimate this quantity. So here, let's estimate. Here is the sort of first crucial thing. So we are going to do a crucial calculation. What I want to draw your attention to is the fact that f prime is a continuous function at a. That means if I am in some small neighborhood around a, then the difference between f prime of x and f prime of a, I can bound it. And I'm going to do that, right? So let us write this. So here. Maybe let's start using some colors over here. So this is can make this small in some in some ball B around A by continuity of f prime at A. And we will do this. Okay. So what I'm going to do now is I'm going to draw a picture over here. This picture is going to become as we go through the proof, this picture is going to acquire more and more parts. So what I suggest is that you draw this picture, and as I keep drawing, then you also continue to draw further, so that you always have this picture in front of your eyes, right, for reference. Okay. So, okay, all right. So here, let's estimate this. So choose a good ball B centered at A with all of the following properties. So one, ensure with all of the following properties. Ensure that for all x in B, f prime of x minus f prime of A, its norm is less than desired epsilon. We will choose epsilon a bit later. Okay, I can certainly do that, right? Okay, very good. And so for later purposes, I am going to write down the next two requirements, because I do not want to keep going back and forth. So for now, just understand the meaning of the requirements rather than why they come in. Why the requirements are there? It will come later in the. Here is the other thing. So I have this function u, f, right, which is from u to f prime. The derivative functions. Excuse me, sorry. So what I want to do is the following. You see, f prime is invertible, correct? Now, this invertible at A. Okay. So how do I check that an operator is invertible at a point? A simple calculation criterion. A square matrix is invertible if and only if its
Determinant is not zero.
This determinant is non-zero. So I am going to compose this with the determinant function, real numbers. Now, Determinant is a continuous function and f prime is continuous at a. So this composite is also continuous. And I know that this composite, so this is continuous at a, and determinant of f prime of a is not equal to 0. So can choose. This is a continuous function. At some point, its value is non-zero. So I can just choose a small ball around that non-zero number so that the 0 is not included in the ball. And I take the inverse image that will contain an open set, right? So in other words, I can make the ball small enough so that f prime of x at every point in that ball will continue to have non-zero determinant and therefore will be invertible, such that for all x in B, determinant of f prime of x is non-zero, and hence f prime of x is invertible.
Sir, actually, we can choose it in such a way such that the sign is also same, right? I mean, throughout the ball, the determinant
We can,
either is.
yeah, we can. But you see, in fact, this will be forced, no? Because if the
Yes, sir,
determinant,
by the
right?
intermediate property, continuity.
Okay. And so later on, the reason why we want to do this is that we will get the condition that f prime of x times some vector is 0. Therefore, we want to conclude that that vector itself is 0. That's how it will be used. Okay. And then the third condition that I want to have is that so you see this okay. By the way, all of these are standard things, and the third one that I'm going to say is particularly standard. See, suppose the set that is given to me, U itself, it satisfies both of these properties, number 1 and number 2. All right. Now, at some point, what I want to do is I want to define a function on this ball, and I want to minimize this function. Can I ensure that a function defined on an open set has a minimum? Do functions defined on open sets a global minimum? Do functions defined on open sets, are they guaranteed to have minimum, real valued functions?
No.
No, certainly not. On the other hand, if I could just make this function to be defined on a closed ball, then because the closed ball is compact, then I will guarantee that, okay, there is a minimum. And once there is a minimum, then I can, or maximum, whatever, then I can analyze it. So for this reason, if I have this function defined on a ball, maybe I can just shrink the ball slightly so that the boundary of this smaller ball is also contained in the original set. So for technical reason, we will do this. So shrink B further if necessary. To ensure that B bar is also contained in U. Remember, U was the domain. All that I care about is that the function that I have can be evaluated on the boundary of this ball. So that I can, whatever function, given function and so some associated functions can also be defined on this boundary. So I can minimize them. So I will say useful later. To minimize a continuous function. On this compact set. So minimum is assured to be guaranteed. So what we should do is now let's draw a picture over. Right? So hopefully make this picture. So this is the point A. This is the point F, right? And in some ways, I don't even want to draw the set U. The set U is really just just something, okay? It's just some ambient thing. So let's draw this. So this is the ball that I have chosen with respect to the given. Okay, it's already my, you know what? So let's. So this is the ball B, and its image is going to be something, okay? But remember, this ball and its boundary, they are both contained in U. So this ball B, and this is the boundary of B. And maybe I should draw you. So something, some quantity, right? So some doesn't really matter. So that is U. The real action is all going to be inside the ball. So this is U. Then that's the boundary. This is the point A. Now, I'm going to have also the image under F of this. So it's going to be something. So this is going to be F of B. F of B. And this is going to be F of the boundary of B. So that partial symbol, that is not to do with the derivative. Okay, that's just the symbol for the boundary of the system. And I don't really need to define boundary of an arbitrary set. You'll see that in topology. Boundary of the ball is just the points where the distance is exactly equal to the radius. Okay. All right. So far I have this, and I will just write down what I have ensured so far by my choice. So for all x in B, f prime of x is invertible, and f prime of x minus f prime of A is less than epsilon. I haven't chosen the epsilon yet, but I can choose it to be whatever. I mean, if some choice works, then any smaller choice will also work. So please draw this picture, and we will refer to this later.
Sir, when we write B, we just mean the open ball, right?
We mean the open ball, right? So I should say this. So choose a good open ball.
Sir, can f of A be on the boundary?
Good question. Can f of A be on the boundary? That's a good point, and it sort of is sort of a stark question that brings into. So what we are going to show is that actually f of A itself has that ball. No, remember, f of A is supposed to have an open set W around it, such that some open set around A maps bijectively to that. So we will see that f of A itself will not be on the boundary. Okay, so actually, is this easy? Is this just obvious? Not really, because you see, for example, if the function were constant, right, then everything is f of A. So what you really want to say, I mean, that question is phrased slightly confusingly, because nowhere am I saying that f of the boundary of B is the boundary of f of B. I'm not saying anything of that kind. The word boundary only applies to the ball. But the underlying question is valid. Is it possible that f of A will also lie on f of the boundary of B? And it can very well happen for arbitrary functions. If the function were constant, for example, or if the function were not injective, then it might be that f of A and f of something on the boundary of B may be the same point. But injectivity will ensure that that cannot happen. So let's prove injectivity. Right? And we have set the scene enough for the sake of injectivity. So let us see where we were. I found this remainder function and I want to see the differences in the remainder function. So R of x1 minus R of x2. So that is what I want to estimate. But now notice what is going to happen. I'm going to estimate this on the ball. Now the ball is a convex set. The function R is differentiable, and very nicely, for the derivative of R, I have a bound. The derivative of R, which is f prime of x minus f prime of a, is less than epsilon. What can I therefore apply?
Mean value theorem.
I apply the mean value theorem. And what does it give me? By MVT applied to R of x on the convex set B, what do I get? So this is the crucial calculation. R of x1 minus R of x2, I get for any x1, x2 in B. This is less than or equal to what?
So epsilon times x1 minus x2 norm.
Exactly. Okay, very good. So now, but I know exactly what R, but I can simply plug in what R of x1 minus R of x2 is, right? So this is equal to the norm of what? F of x1 minus f of x2 minus f prime of a applied to x1 minus x2. Okay, excellent. Now this is yeah, hopefully it will not be so I want to bound this, right? But so recall. What can I say about the norm of p minus q by triangle inequality?
Greater than or equal to norm of P minus norm of Q.
This is just triangle inequality. If I take, because P is the sum of P minus Q and Q. So that's what I'm going to apply. You see, if I want to have the chain of inequalities, then the term on this term that I have written over here, this term, I want to show that it is greater than something, right? So I want to. Okay, so this is greater than or equal to, what shall we say? Now it's a subtraction of two things, correct? So which one should I subtract?
Sir, shouldn't there be an absolute value in the inequality that you wrote? Norm of P minus Q.
Okay. So sorry, greater than or equal. I think this is what you meant, right?
So I mean, if it will be greater than the absolute value of the difference of norm of P and Q, right?
But does it matter? It's greater than sign, right? It might be a negative number.
Yes, I mean, it will be meaningful more if we put the norm.
Right. But you see, the point is, it doesn't matter whether I'm doing P minus Q or Q minus P, right? It's true for both of them.
Yes, sir.
Right?
Yes.
So the way I want to do this is that I want to have this is greater than or equal to This is the way I want it. And the reason for this is that, see, unfortunately, whatever I wrote on the line below, I should have written it to the left so that I could have just taken the cascaded inequalities. So what is the upshot? What do I get?
We can get a lower bound for f of x1 minus f of x2.
Exactly. So the interesting thing here is f of x1 minus f of x2. And what is the inequality sign now? Because I have taken f of x1 minus f of x2 on the other side. What is the inequality?
Greater than or equal to.
It's greater than or equal to, and this is an exclamation mark here, right? Because you see, I want to show that a function is injective. So if I show that f of x1 minus f of x2 is greater than 0, whenever x1 minus x2 is non-zero, whenever x1 and x2 are unequal, then I'm done. So this is good. But what is there on the other side? Let's take a look. This is, now what do I get? F prime of a x1 minus x2, and then
Minus r of x1
minus, exactly, minus this epsilon times x1 minus x2. So let me just say this up short, because you have to do a little bit of rearranging. X1 minus x2, the norm of x1 minus x2. Okay. At this point, okay, so at this point, if I had normalized f prime of a equal to identity, life would have been very nice. Why? So this is remark. So this is in parentheses. What would I have got? F of x1 minus f of x2. What about it? This f prime of a, just the term just drops because it's the identity, right? So on the right hand side, I have the norm of x1 minus x2 minus epsilon times the norm of x1 minus x2. So what would I get? Greater than or equal to?
minus epsilon times
The norm of x1 minus x2. And now I can say, taking epsilon to be anything less than 1, gives me injectivity. Right? Just notice, this says that whenever x1 and x2 are different, then the right hand side is a strictly positive number. And f of x1 minus f of x2, that norm is greater than or equal to this positive number. So those two things cannot be equal. Okay, so I'm stymied a little bit because of this f prime of a. Can I just take f prime of a as a common thing outside? Can I just say that norm of f double prime of a is, so just think about it. It's not a number, right? It's an operator. So can I take it out?
An operator normal.
Yeah.
Yeah, but think carefully. If I take it out as in terms of the operator norm, which way does the inequality go?
I think we can't use operator norm. We have to take like the minima of the, the sphere is compact. So, and then we take the minima of the image,
Fine,
like
okay.
the distance from the
So
origin.
let me just, you see, what I need to do is I need to put something over here. So this is what we need. In order to make this, here. I need to do this. You see, if I take the operator norm of f prime of a, the inequality goes the other way around, right? T, if I have an operator T, then T applied to U is less than or equal to the operator norm of T times the norm of that vector U. But the solution that he just proposed is perfectly good. What I need to do is I need to find a lower bound on f prime. And the lower bound of f prime of a is going to be, the lower bound on the factor by which f prime of a will change the norm of any vector. So in our case, we need to find a lower bound of on f prime of a times x1 minus x2. But this is all right. Minimize f prime of a u on this on the unit sphere. Sorry, let's also just put the norm over here, because so minimize so this is compact, right? So this is a compact, and this is a continuous function of u. So I have the minimum. So minimize this. So let's say minimum is equal to m. Why can't this minimum be 0?
Because it's invertible.
Correct. So greater than 0, because f prime of a is invertible. So f prime of a of non-zero u is not equal to 0. And remember, this is I'm minimizing on a compact set, so the minimum is actually achieved. Okay, all right. So I have this minimum, let's say m. So what do I do now? What do I do for epsilon? Choose epsilon to be
Lesser than m.
less than m, and then I'm done. Oops, epsilon less than m. And then for the resulting ball B, we have not for. In the resulting ball B, we have, let's write down this final because this is important. F of x1 minus f of x2 is greater than or equal to m minus epsilon times x1 minus x2. So this is important. Let's write this down. And m minus epsilon is greater than 0. So this is injected. All right, very good. So but we can actually get something more than this. You see, the sign of this inequality is very nice. It is going to help us. I mean, it helped us for injectivity of f on b. So what do I have? So I have bijection from where to where? Certainly from b to f of b, I have a bijection. And let me just call this f inverse, which I have called g. So I have this bijection. Can I say anything talk about continuity of F inverse without knowing what kind of set F of B is? The answer is yes. Because what kind of set is F of B? Wherever it is, whatever it is sitting inside Rn, right? I have the distance function on Rn. So F of B is a metric space. For all I know, it might be a horrible set, but it is still a metric space with the usual metric on Rn. So it makes perfect sense to talk about continuous functions from that. Is it, no, can we say anything about continuity of this function G?
Yeah, we can substitute like in the relation we just got.
Exactly. So just look at this relation star, what it is saying. So, star is saying any y1 equals f of x1, y2 equals f of x2 in f of b says for, what does it say? Let us just say, so this is going to say y1 minus, and let's flip. So it says that, so let's write this on everything, i.e. g of y1 is equal to x1 and g of y2 is equal to x2. But remember, y1 and y2 are arbitrary, right? So what is this saying? Let's flip the inequality. So x1 and x2, so we have g of y1 minus g of y2. And which way does the inequality go now? This is
Less than or equal to.
less than or equal to 1 divided by m minus epsilon times y1 minus y2. This tells me that if y1 and y2 are close, then I can make g1 and g of that ensures that gy1 and gy2 are also close. So in fact, this is not giving me not only that the function g is continuous, but in fact it is uniformly continuous on the ball. So says that, i.e. maybe a semicolon, never mind. So i.e. G is uniformly continuous on continuous on which set? On f of b.
FB.
Okay. So right now I have no idea what the set f of b is like, but I know that. Okay, so now we come to part 2. Okay, so we need to get a move on. Let's see what we have achieved so far. Let's look at the statement way back. By the way, so 3 is a separate thing, and 3 is actually one of the maybe the easiest part of it. So in number 2, what is left to be done? Do I have a bijection? F is a bijection between some sets? Yes, I did. It is bijection between B and f of B. Now this set V is supposed to be open, but I have taken it to be a ball, so it's good, no? So it is open. And the inverse of this map F, which I have called G, is also continuous. So I have done that. So what is left? Is anything left?
We need to make sure that FB is open.
Yeah, and there is no reason for f of b to be open a priori, right? So we need to show that in the target I have an open set which is contained in this target. Because if I have an open set contained in the target, then I can take V to be just its inverse. So let me write this. So step 2. To show that F is a local homeomorphism, it is enough it is enough to find a ball, and so let's say an open ball. W around A with W contained in f of B.
I think FB itself is open by that topological definition of continuity applied on G.
But you see, open in what, right? See, the word open really depends on which set I'm considering. So when I say open, I mean open in the ambient Rn.
Yeah, I see. Yes.
Right. So there is real work to be done over here. And by the way, it will no, let me not say anything more, because okay. No, I was about to say that f of b will itself turn out to be open, but I'm not sure about that, because we have assumed the continuity of f prime only at a single point. So I'm not sure about this, but what I'm saying here is it will do the job. Okay, so then we simply take V to be what? Remember, F is supposed to be a bijection between V and W. F is already a bijection on B. So all along
Just
I'm
take W.
So if I just take F inverse of W. Do I have to worry about whether V is open now? Now that I ensured that W is open. If once I ensure that there is such a W, do I have to worry about V being open?
No, because F is
No.
continuous.
Because F is continuous, right? So this is okay. Which is open by continuity of F. And clearly VFW is a bijection. Just, or I should say just G, are bijections. Just restrict F and G from B and F of B respectively. Okay, so this is really the fact that how do I find this W? And this question that was asked earlier will come into the picture. We can use this. So let's go to the picture over here. So what was the question that was asked? That is it possible for this f of A to be in f of the boundary of B? And now we have shown that that is not the case, right? If you want, maybe what we can say is that make B even smaller than make B even smaller than where I have shown it to be a bijection, so that even the boundary is contained inside a set on which I have a bijection. But this sort of brings in how close can f of B, how close can f of A be to this f of the boundary? And the answer is it really cannot be very close. This is where this idea that I have a function, compact sets are good. That's in order to while talking about minima or maxima of continuous functions, it is good to deal with compact sets. So the starting point is this question: how I want to put something around f of A that is totally contained inside f of B. So how do I find the radius? My beginning thought is that let me try to ensure that this radius will keep me away from f of the boundary of B. And that is okay, because what I can just do is, so please think of, please look at the picture while I'm doing this. So what radius to take around W? So the idea is to stay away from f of the boundary of B. So what do? I just look at what does it mean to take points that stay away from the boundary. Well, let me see how far the boundary is. So let us look at the function f of x minus f of a. Where are the points x? That's precisely what I'm looking at, right? I'm looking at all the points on the boundary of this ball B. I'm seeing where they go, and I'm looking at how far they are from A, how far they are from f of A. By injectivity, we already know that this function is so compact set, and this is a continuous function. So I can take its minimum, and I can call this delta. And I know that this minimum is greater than 0 because of injectivity of f. So maybe what I should have said earlier is that I really want f to be, so this B bar is contained inside. Maybe I want to shrink the ball even a bit smaller so that even on B bar it is injected. So injectivity of f on B bar. Okay, so this is, so I hope things are okay. Let me draw.
Why must the boundary of B get mapped to the boundary of FB?
I never said anything of that nature.
I see. Okay.
Right? The word boundary of f of B has never entered our consideration.
Yes.
Yeah. Okay. So remember, x is in the boundary of B. That's all. I'm simply taking f of all of those things. Injectivity of f on B bar. That means that f of none of those x's is equal to f of B. So therefore, so this function is always a positive function, continuous function of x. Okay, very good. So what should I choose the radius of W to be r. Oh, sorry, this I used a function r earlier. Sorry, this is a constant r now. But I want to stick to r because I don't want to deviate from my notes. What should I choose this r to be?
Less than delta.
Less than delta, but for some later estimate, I want to make it to be half of delta or less than half of delta. So this is what we do. Okay. Great. So let us now do this in the picture here. So this distance is something, and now let's use some other color. So here I choose this ball. And in fact, my ball is slightly bigger than, but okay, schematically this is okay. So this is R, and R is less than half of delta. Okay, very well. What I want to say is that this, so this is W. Now, of course, the way I have drawn the picture, it's already a lie, right? In the sense that I haven't proved this. I drew this nice picture, this green ball inside f of B, but that's something that I have to show, right? And let me just draw over here. So this is going to be after the fact that So this is going to be F inverse of W, which is equal to V. So what I have to show is that by definition, this W is totally inside F of B. That's what I need to show, right? To make this picture a truth. So need to show or not need to show, will show. Will be done by showing. If we show that W is inside F of given any C in W, there exists X star in B such that F of X star is equal to C. So I'm fixing such C, okay? Fixing some C, and my point is to find such X star. By the way, X star is necessarily unique. Why?
Injective.
I injected. So where am I going to find this X star? And this is where sort of the thing comes in, right? So idea. Oh, okay. So we are just about out of time. So let me at least just formulate the idea, okay? And then we can start idea. So I want to show that a given point is among a list of points. That is, the point C is among the list of all the F of X's. So what do? I consider the distance of C from all possible F of X's. So let's write this down. Consider the function from B to, okay, so this function X, what does it go to? It goes to F of X minus C. So of course this function is to, so this function, by the way, it's a continuous function. In fact, it's a differentiable function, right? Sorry, just 1 second. No. This function will not be differentiable. See, the norm function is not differentiable, no? Just take absolute value. But how do we make this function differentiable? There's a very simple way to change this function to make it differentiable, and in fact, even more convenient. Notice what I want to do is I want to minimize this function. And I want to show that the minimum value is actually equal to 0. That this function takes 0 value. So to show that the distance is 0, it is equivalent to showing that the distance square is 0. Consider and the differentiability is coming really because of the square. Okay. So what I mean, we'll write down the formula, but let me not do that now. So idea, consider and show that this function takes value 0 by minimizing it. No, sorry, just 1 second. 1 second. I'm a bit confused over here. Yeah, to show that, okay, by minimizing it. Okay, so now this function is defined on a ball. Is it clear that the function will have a minimum? It's defined on an open ball. All right, come on. So let's finish this off. And in fact, I'm sorry I got into differentiability. That will come later. This is a continuous function, right? In order to show that this function takes a minimum, what am I going to use now? This is the continuous function. And let's get rid of the square and we'll bring it in later. This is a continuous function because f is continuous, subtraction is c is continuous, and norm is continuous. But I do not know that this continuous function will take a minimum value on an open set. So I play the same game once again. I extend the function to v bar by minimizing it on v bar. And then we will show that this minimum value actually cannot occur on the boundary. It will actually occur inside. Minimum boundary. That at interior point x star where minimum occurs, we must have so a function has minimum at an interior point of a differentiable function. What must happen? Derivative has to be zero. Derivative has to be zero. Which will give that f of x star actually equal to c by a simple calculation. Using invertibility of x. So I have just laid out the calculation. But for today, we should just stop with this and we'll finish the proof on Monday.